Welcome to the second half of this presentation. Um, I got a 15-minute limit on the first one due to a licensing issue for this software, so I'm picking up where I left off. We're talking about stream groupings and the importance of the tasks in one bolt sending their output to specific tasks in a downstream bolt for the word counting application that I'm doing. I think we covered that sufficiently in the last video. Here's a good picture of the whole thing. If you look at bolt A and bolt B, let's say in shuffle grouping, bolt A can send its output to any one of these three randomly selected, so it'll be pretty even. In fields grouping, bolt A would say only send it to task 2 for the word cat, whereas the word dog might go to only task 1, the word skunk might go to task 1 only, and so on. Very similar to the way Hadoop works with map and reduce. It's very similar. My application. The application I did I did all the development in Windows 7 using Eclipse. I ended up with 6 Java source code files. I downloaded some Storm libraries. I got some Twitter for J libraries. And since Storm only runs in a Linux environment, I had to what I did is I built everything. I did all the development and built everything in Windows, and then packaged up a jar file and then transferred it over to my CentOS VM. Very similar to what we did with our Hadoop MapReduce projects back around assignment 6 or 5 or in that area. In fact, the command line to run Storm is very similar. I guess maybe all these big data applications all kind of use the same model. You get a jar file, and you know it'll look eerily familiar to what Hadoop does. But that all worked great. Here's a picture of my development environment. I love Eclipse so much I just couldn't help putting a picture in. There it is. One of the looks like one of the bolts I'm working on there. My application, the details of my application. I got 6 source files, as I mentioned. I have a topology, which I call the Twitter topic topology. It includes the main method that defines a topology, creates and associates spouts and bolts. Basically builds the whole directed graph structure. I define stream grouping. I define the stream grouping types and how many tasks to run for each bolt. And I set the cluster to run in local mode as opposed to distributed mode. And then I submit the whole topology to Storm for processing. I didn't mention this before, but Storm, like Hadoop, can be run locally or in a distributed environment like AWS. When you run it locally, Storm is basically simulating the distributed environment, much like the way Hadoop does when we run it locally. My spout, I need a spout to get the data, which I call a Twitter spout. It establishes connection to Twitter streaming data source. It passes the command line parameters that come in through main are passed into the spout, and the spout uses them to configure the Twitter data stream. It also sets up a listener that is triggered by incoming data, and I use a Java concurrent package class called the linked blocking queue, which is a nice way to kind of buffer the incoming endless stream of tweets plus the outgoing endless processing. It's sort of a nice way to keep things nice and smooth. You don't have anybody waiting on anything. The queue gets filled up and kind of goes up and down, but and it seemed to work quite well. I also have 4 bolts. I have a filter bolt, which is the first bolt to receive data from the Twitter spout. It extracts the text of the tweet. It figures out what language it is, and it normalizes the text. It also strips out any URLs and strips out all punctuation, and then sets everything to uppercase. So I'm basically always comparing uppercase text. I don't have to worry about lowercase text or anything like that. And then if the tweets aren't in English, I just ignore them because, the ones that are in Arabic and Korean and Japanese, I don't know what to do with those. So I just throw them out. No offense, I just don't speak those, and I wouldn't know how to filter them. So I was getting a little bit late here, sorry. And then I have the word mapper bolt, which simply breaks a tweet into tokens and then passes the tokens one at a time in a tuple downstream. And downstream from the mapper is the word reducer bolt, which receives the tokens, counts them, and then stores the count in a local task local map. Now, I could have just omitted, written out all the stuff being stored in those maps from that point, but I decided to pass the actual current value and the current word and its latest count down to another aggregating bolt, which I'll get to in a second. That's what I mentioned. I already mentioned this, but I use the field grouping on the output word from the word mapper bolt, so the word reducer bolt tasks would always get the same set of words, and none of them, there's no tasks that have a map with the same word and some count in them. This just keeps the counts accurate because only one task is aware of a particular word. Alright, this is the output handler bolt. It's kind of extraneous, but it was actually kind of interesting to write. What I do with this one is all the word reducer bolts can send, say however many there are of them, they all send in a tuple which is a word and a count, and the count is the latest count from its own local map of how many of that word there are. So I take all of these and I have a class or a static, class level map, sort of a global map in this class, which combines all of those all of those separate maps from the tasks at the word reducer bolt level, and builds a giant global list of all the words and all the counts. And then for every 200 words that are processed, I dump that map to the console so I can look at it, see how the counts are going. And because this is a multi-threaded application and this map is declared as a static class member, and it's accessible by all of the output handler bolts tasks, I needed to put in some synchronized blocks on the map access to prevent concurrency issues. Sort of standard Java multi-threading. Okay, here's the application finally. This is the start of the application. You can see here I've got the command line, which is outlined in the Word report I have. I'm looking for the phrase Iron Man, in reference to the Iron Man movie which just came out, and I'm running this for 60,000 milliseconds, which would be a minute. So off it goes. It's echoing out the filter phrase, which is Iron Man, and the running time, which is 60,000 milliseconds. Here we are in the middle of execution. Here's a bunch of, I echo the text from the tweets because it's quite entertaining, actually. Here's one that says, yeah, Iron Man 3 was freaking fantastic. So I heard Iron Man 3 was good. Let's see. Let's see how Iron Man 3 is in 3D. So why haven't I? So I haven't seen Iron Man 1 or 2, but I want to see 3. Haha, judge me. So you get the idea. It's Twitter. There's all kinds of crazy stuff. When I ran this for about 10 minutes, I got lots of positive word counts like good and awesome and wicked, great, and all this stuff. So I concluded that Iron Man was a good movie just based on these tweets. So, excuse me. And here's the, after 200 words have been processed, here's the output. And you can see here the word iron appeared 16 times, and the word man appeared 15. So it must have processed approximately 15 or 20, 15 or 16 tweets that had, obviously those words, because those are the ones I was telling Twitter to give me tweets that had definitely had those 2 words in it. And then all the other words, it's just matching them and building counts for them. Like the word good is in here. The word with is here twice. As time goes on, obviously you get a lot of junk words like with and the, but the important words like positive or negative will start to add up too, and then you can kind of make some determinations from that. Of course, this would work for any input word or phrase you want to look for. I think, what do we got next? Oh, this is the application finishing. So after a minute, what happens is when the main thread starts the application, it goes to sleep for whatever time I specify, in this case 60 seconds. So it goes to sleep, the rest of the topology runs and does all its processing. And then when the main thread wakes up, it immediately shuts down the topology and kills the cluster. So that's how it ends. In fact, shutting down in process zookeeper. So it's basically at this point it's already shut down. It's already begun to shut down off screen, and now it's shutting down the zookeeper, which is that middle layer that allows Nimbus and supervisor to talk to each other. And now then everything finishes and it goes back to the command prompt. So that's the last one. So there it is. In conclusion, I'd say Twitter is a lot more awesome than I thought it was, and Storm is even more awesome than that. It's really the sky's the limit with things you can do with it. I was trying to I thought of 100 different applications you could use. I was thinking about maybe getting real-time earthquake data and figuring out where all sort of make a view of the Earth and what's shaking real time. Things like that. There's so many things you can do with this. Probably like when Hadoop first came out, people thought of a million things you can do with it. Anyways, I really enjoyed this project. I really enjoyed this class, and hope everyone has a great summer, and look forward to seeing some or all of you again in the fall. All right, take care. This is Eric Jansen, signing off.